So this is a lesson on our last section of our sequences and series unit. So this lesson's on geometric series. But before we get there, let's do a little warm up about arithmetic sequence and series. So again, remember arithmetic sequence was a sequence of numbers where there was a constant difference between each of the terms, and an arithmetic series was simply the sum of all the terms of an arithmetic sequence. So in this example, we're given a 10th term of an arithmetic sequence is 34, and the sum of the first 20 terms is 710. And from that information, we want to be able to determine the 25th term. So it doesn't seem like we're given enough information to sort of solve this, but we sort of have to just break down the problem into two steps. So first thing is that we're told that the 10th term of the arithmetic sequence is 34. So again, the general formula, general term for arithmetic sequence is T of n is equal to a plus n minus 1 times d. And in this case, we're told that the 10th term, so that means n is 10. So the 10th term is, well, we don't know what the first term is, and then n is 10, so that's 10 minus 1 times d. So we're told the 10th term is 34, so that's where we could place t of 10, just like we could play as f of x or something if we know what f of x is. So in this case, we know what t of 10 is, that's 34, and here we get a plus 9d. So we can't go any further with that piece of information, but thankfully, this is why we're supplied with a second piece of information, and the sum of the first 20 terms is 710. So if we go back to our arithmetic series formula, we get S of n. So remember I gave you two formulas to sort of to deal with arithmetic series. So one was n times the first term plus the last term divided by 2. In this case, we're not given the last term. So here we have to supplement the general term back in for the last term. So our formula becomes n times 2a plus n minus 1 times d all over 2. So in this case, we're told that the first 20 terms is 710, so that means n is 20. So here s of 20 is equal to 20 times, again, we don't know the first term, so it's 2a plus 20 minus 1 times d. We don't know the common difference, all over 2. So s of 20, we're told is 710. So I'm just going to simplify 20 divided by 2 is 10. 2a plus 19d. And here I just want to sort of expand this. So here I get 710 is equal to 20a plus 190d. And it looks like I could probably divide everything by 10. So here I get 71 is equal to 2a plus 19d. So here I have two equations now that I can go off and solve for. So let's call this equation 1 over here and equation 2, and I'm going to solve this by elimination. So I need 2 of the first equation. So that's going to give me 68 is equal to 2a plus 18d. And then I just only need 1 of the second equation. So in this case, that's 71 is equal to 2a plus 19d. So I'm going to subtract these two because I'm going to eliminate the a's. So 68 minus 71 is a negative 3. The a's cancel out, and 18d minus a 19d is a negative d. So dividing both sides by negative 1, or multiplying both sides by negative 1, we get d is equal to 3. So we know the common difference here is 3. So we need to go off and find out what the first term is, get what a is. So I'll plug that back into maybe the first equation. So here I'm going to get 34 is equal to a plus 9 times d, which is 3. So 34 is equal to a plus 27. So subtracting 27 from both sides, I'm going to get a is equal to 7. So here I know that the first term is 7. So going back to the original question, we want to determine the 25th term. So here we go back to a general term formula for an arithmetic sequence. So that's going to be t of n is equal to a plus n minus 1 times d. In this case, we want the 25th term. Well, now we know that the a is 7 plus 25 minus 1, and the common difference is 3. So t of 25 is going to be 7 plus 24 times 3, which is 7 plus 72. And then that makes t of 25 is equal to 79. So here we discovered the 25th term in that sequence, even though we weren't given a lot of information about it, but we'll go off and determine the 25th term is 79. So that's how we could do an example like that. It was a nice little review of arithmetic sequences in series, because we sort of have to go back and remember what our general term was for arithmetic sequence, and then coming back and also remembering what the formula for arithmetic series. So to just start off with today's lesson on geometric series, let's look at the success criteria. Simple, we're just going to determine the series of a geometric sequence. So again, series we started to discover from the last time. It's just sort of a fancy word for sum. So here we're going to really calculate or determine the sum of the terms of a geometric sequence. So I like to start just with just a real life example. So I don't know if you guys are familiar with chain letters. So back in the day when people used to mail letters, this was one of the things that was really kind of not pleasant that was going around. I guess the electronic version or digital version these days would be spam or chain mails through email, which used to clog down the internet a lot. So if you ever caught sort of initiating chain letters through email or viruses in some sense, that's a federal crime from what I understand. Because it does bring down systems and it brings our infrastructure to a halt a bit. So here we can discover a chain letter. So usually this is a letter that gets mailed out to people, and they get it, and they're required to make certain copies of that letter and mail it to different people within 24 hours, or something bad will happen to them, most likely death, or they become poor, their mother might die, or something. So this is sort of a try to scare people to sort of forwarding on this letter so that bad things don't happen to them. So we'll take a small example. Usually in chain mails, they say they have to mail to 10 people. But in this case, we're going to keep it small. And we're going to say, well, 3 people initially receive this chain letter. And each person who receives it after that follows the direction of mailing to 4 people. And they all do that. How many letters will have been mailed after 7 days and after 15 days? Well, let's start off with 7 days. And let's do a calculation based on that. So here, what we want to do is calculate, the very first day, 3 people has got it. And then what they have to do is each of them has to create 4 of these letters and then mail it off. So 3 of them do it to 4 people. Afterwards, we're going to get 12 letters sent out and 12 people receiving this letter. Now, each of these 12 people are going to create 4 copies of this letter and mail it to 4 people. So in this case, 12 times 4, we're going to get 40 letters sent out on the 3rd day. And then we keep seeing this pattern that basically we keep multiplying this by 4. So the next number in our sequence is 192 on the 4th day. And then 192 times 4 is 768 on the 5th day. 768 times 4 is 3,072 on the 6th day. And finally, on the 7th day, those 3,072 people are going to mail, each of them going to mail 4 people this letter. And on that last day, 12,208 letters are sent out. So this is our geometric sequence. And what we want to do is really want to add them all up to find out what's the total number of letters that got sent out. So really just going to add them all up. If you take out our calculator, and the sum of these numbers is 16,903. Okay, so that's how many letters got sent out over 7 days. A grand total of 16,903. So in order to answer the question of 15 days, we could continue listing off additional terms in our geometric sequence and add them all up, and we'll get a certain answer there. But of course, I could also extend this problem, so that's not so easy. So after 1 month, how many letters were sent out after 2 months, and heaven forbid, even after a year? We can see that hopefully once we get to 15, you can hopefully see that we never want to ever reach, never mind a year, but not even a month. So hopefully this chain letter stops after a month. I mean, sorry, after 15 days, even after 7 days is a manageable number right now. So in order to explore a formula to do this, I'd like to show that to you, just like what we did with the arithmetic sequence, where we sort of listed out the arithmetic series in order, and then we listed it backwards, and then we noticed that if we added up the 2 rows, the sums of the rows came out to be the same. So that's how we sort of derived that neat little formula. So we're going to do something similar in terms of a geometric series. So in this case, as an explicit example, because we have 7 terms here, so we want to calculate the sum of 7 terms. So in this case, we got 3 plus 12 plus 48 plus 192 plus 768 plus 3,072 plus 12,208. And here, the common ratio in our sequence is 4, because it's 4 letters. Each person is mailing out 4 additional letters. So the common ratio is 4. I'm going to take my entire series and multiply by that the common ratio. So in this case, 4. So I want 4 times s of 7. So essentially what we're going to do is going to go to each of our terms and multiply by 4. So here, we're going to get 3 times 4 is 12. So I'm not going to list it above the 3, because even though it's the first one, but I'm going to slide it over a little bit and list it there. So 3 times 4 is 12, and 12 times 4 is 48. So 48 times 4 is going to be 192, and we can continue each of these, and we recognize that we're going to get the same numbers. 3,072 plus 12,208. But then we also need one last term in this case, 12,208 multiplied by 4, and that's 49,152. So the neat thing about this, because we got the same terms here, is we're not going to add them up, but we're going to subtract them. So here I want the difference between 4s7 and s7. So a little bit like what we did with elimination there. And here we can see that because we got the same terms over there, so here we got 3s7, because 4s7 minus s7 is the 3s7, is that these things are going to cancel out when I subtract them. So really what am I left with is, well, 0 minus a 3, that's going to be a negative 3, plus, oops, I should have crossed off 49,000 because we still need that, plus 49,152. So 49,152 minus 3 is 49,148. So that's 3s7. So in order to get s7, we're going to divide both sides by 3. And so s7 is 49,148 divided by 3. Plug that in the calculators, and lo and behold, we get 16,903. So the same answer as if we did it by hand. So how can we sort of say this in general? So in general, if we have a series, so let's say S of n, and we want to multiply this series by the rate common ratio, so here we're going to get R, S of n, and we want to take the difference of that. Okay? So in this case, what happens is we're going to get, because we got 0 minus the first term, this is really minus a. And then because we get all this done out, really we're going to get this last term. So what was our last term? Was 12,208. But again, what's our term in a geometric sequence is a to the power of Rn minus 1. And then we want to multiply that by R, because that's what we did over here. We took that last term, we want the next term in our sequence, so we have to multiply that by R. So here we're going to get simplify this on the right side is going to be minus A plus A R to the power of N. Notice that here, and this trick is going to come in handy later on, but notice here, this is the term after the last term. Because the last term of our sequence is a to the power of a times r to the power of n minus 1. But if we multiply by r, we really get the next term in our sequence. On the right-hand side, or sorry, left-hand side, we're going to factor out s of n. So we factor out s of n. That's going to be r minus 1. And in order to get s of n, we're going to divide both sides by r minus 1. So here, we're going to get, and just copy the numerator here, or sorry, the right-hand side, by r minus 1. So let me just sort of rearrange that side. This is going to be a r to the power of n minus a all over r minus 1. And finally, on the right-hand side, let's factor on a. So we get r to the power of n minus 1 over r minus 1. So there's our general equation or formula to find out this series of a geometric sequence. Okay, so this was a little bit tricky because it looks like it's almost the same in terms of the numerator and denominator, but there's a huge difference in the numerator. R is to the power of n, and on the denominator it's just r minus 1. So a lot of people might be tempted to reduce that. It's not the same. In fact, we're going to discover it's not even close to being the same. Okay, so that's our general formula to go off and determine the series of a geometric sequence. But what's really nice is here is that you can think of this in general. Again, this is why I wrote this over here, is we're going to take the term after the next term, or the last term, and we're going to subtract the first term. And then we're going to divide it by r minus 1. So that's really a quick way that we can discover the sum of the series. So by definition, a geometric series is the sum of the terms of a geometric sequence. Nothing earth-shattering. I'm sure you anticipated that coming. So here is the formula that we have derived. So again, this is what I kind of said before. Really, we're going to take the last term and find out what the next term is by multiplying by r, and we can know what that's going to be because it's a geometric sequence. Subtract the first term, and then we're going to divide it by r minus 1. When we expand everything out, there's our general formula where it's s of n is equal to a times r to the power of n minus 1 divided by r minus 1. And something that I guess should be stated, even though it should be obvious, is that we can't have a ratio of 1. Because if r is 1 in here, first of all, is it philosophical? Is it even a geometric sequence? I guess so. R is 1, but we can't add it up in this case because we're going to divide by 0. So we can't use that formula when r is equal to 1. So let's go through a couple examples. Oh, well, let's finish off this other example. So we want to look at S of 15 because we want to know what's happening after 15 days. So how many letters are sent out? So we take our formula now, a r to the n minus 1 over r minus 1. So in this case, we said that a was 3, the common ratio was 4, and in this case we want 15 days. So in this 15, so S of 15 is equal to 3 times 4 to the power of 15 minus 1 all over 4 minus 1. So in this case, S of 15 is 3 times 4 to the power of 15 minus 1 over 3. So luckily in this case, we can actually reduce to 3. So S of 15 is actually 4 to the power of 15 minus 1. You take that in, plug into your calculator, and we're going to discover it's a huge number. So even after 15 days, we get 1,073,741,823 letters that got sent out over the span of essentially 2 weeks. So here was a little bit of an example of how fast exponential growth is. And in this case, after 15 days, our entire mail system would be bogged down because on really 1 billion letters is a lot to process. Okay, so that would be the answer to that question over there. So let's look at some more explicit examples of just practicing our formula. So in this case, we want to look at, we want the sum of the first 10 terms, essentially S of 10, for each of these geometric sequences, where in this first one, we're given the first term is 80 and R is 2. So it's really just a straight application of our formula. So again, S of n is equal to A times R to the power of n minus 1 all over R minus 1. So we want, so n is 10. We want the sum of the first 10 terms. So S of 10 is equal to what we're given, A, which is 80, times R, in this case 2, to the power of n. So 2 to the power of 10 minus 1 all over R minus 1. In this case, R is 2. So it's just going to be 2 minus 1. So S of 10 is going to be 80 times 2 to the power of 10 is 1,024 minus 1. Well, 2 minus 1 is just 1. So in this case, we get 80 times 1,023. And 80 times 1,023 that's going to be 81,840. Okay, so let's do the next one. So really it's the same type of question, except that here R is negative, so it's a little bit more tricky in this sense. So here we're given S of n is A times R to the power of n minus 1 all over R minus 1. So here we want the 10th sum of 10 terms. So A is 5. The common ratio, so we need to make sure we put the negative 3 in brackets, all to the power of n, in this case which is 10, minus 1, and R is negative 3, minus 1, so here we can see that the denominator is actually negative 4. 5 times, well, negative 3 to the power of 10 is 59,049 minus 1. And once we work all that out, our final answer is negative 73,810. So our next question, we're giving the sum, we want to determine the sum of the series. So here the difficulty is that we do not know how many terms are in this series. But we are sort of given the last term. So let's go off and sort of calculate this. So S of n is equal to A times R n minus 1 all over R minus 1. So in this case, let me write this out. A is going to be 17. In this case, the common ratio actually we keep multiplying by negative 3. And we do not know what n is. So let's do our best. In this case, S of n is equal to A, which is 17. R is negative 3 to the power of n minus 1 all over negative 3 minus 1. So because we're given this term over here, we have to use our geometric sequence equation to figure out what n is. So our geometric equation T of n is equal to a times r n minus 1. So T of n, in other words, the nth term is negative 3, 3, 4, 6, 11 is equal to a, which is our first term, is 17. We know our common ratio is negative 3, and to the power of n minus 1. So here we want to isolate for our power, so we want to divide both sides by 17. So I'm just going to write negative 3 to the power of n minus 1. So 3, 3, 4, 611 divided by 17 is negative 19,683. So now we have to go off and solve for the exponent. So we have to go back to our lesson on exponents, and in this case logs. So we remember that if y is equal to b to the power of x, right? If we want to solve for x, in other words, we want to find what the exponent is, we actually take the log of our answer, in this case log of y, over log of my base. So in this case, we know that n minus 1 then is going to be log of my answer, in this case negative 19,683 all over the log of minus 3. Now if you go off and plug that into your calculator, you're going to get some errors because the log is negative. So didn't have time to go over it, and nor am I going to explain it now, but really could turn these into positives. So here n minus 1 is going to be the log of 19,683 all over the log of 3. And we plug that into calculator, we're going to get n minus 1 is equal to 9. Okay, you must get an integer answer. If you did not get an integer answer, then something went wrong. So in this case, adding 1 to both sides, we know that n is 10. So coming back to originally what we want to do here is really want the sum of the first 10 numbers. So in this case, it's going to be 17 times negative 3 to the power of 10 minus 1 all over, well, minus 3 minus 1 is negative 4. And if we go off and plug that into our calculators, let's do 17, well, let's do negative 3 to the power of 10 first. That's 17,000 times 59,049 minus 1 divided by negative 4. So 17,000 times 59,048 divided by negative 4. And we're going to get the first 10, the sum of the first 10 terms is negative 250,954. Okay, but hopefully you were paying attention. Remember, whoa, couldn't we use that other method of taking the next term, adding it to the first term, subtracting from the first term, and dividing by r minus 1? Wow, let's try that. So in other words, we're going to take the term after our last term, subtract the first term, and get r minus 1. So here we know that t of n, our last term, was negative 3, 3, 4, 6, 11. So the next term after that would be that times negative 3. So I'm going to take it out my calculators. So negative 3, 3, 4, 6, 11 times a negative 3. So the next term in that sequence would be 1,1003,833. So here we're going to take 1,003,833 minus the first term. So what was the first term? Was 17. And take that and divide it by r minus 1, so negative 3 minus 1. So essentially this is minus 17. So essentially this is 1,003,816 divided by negative 4. And lo and behold, we get negative 250,954. So, given a question to solve, I use either one, but recognize that hopefully you can see that you actually want to prefer to use the second one. The cool part about this is that you do not need to know n. In other words, you don't actually need to know how many terms in this sequence or this series in order to add it all up. So that's pretty cool. Just one last question. Used to do shuttle run in gym class all the time. For those of you guys who don't know what a shuttle run is, basically you run to a certain distance and you come back. Usually you have to start on the ground. You have to touch the line, start with your nose on the ground. You get up, you run, touch the line, and come back. So in this case, Rhonda starts from one line. She runs 1 meter forward, and then she returns to the starting line. Then she turns around. She runs 2 meters forward again. So go 2 meters this time, and then she comes back and touches the line. She turns around, now runs 4 meters forward, and then comes back, and so on. So if her last run in the shuttle run is 60 meters, what is the total distance that she's covered? Well, we could see that our sequence or our series is, well, she goes 1 meter and comes back, so that's 2. Then she does 4, and then she does 8, and then she does so 4 there and back, and then she does 8 there and back, so that's 16, and finally she does 16 there and back, so that's 32. So in this case we have 5 numbers in our term, so we really want to do S of 5. So we're going to break out, so let's go back to our original formula, because that's the one we're probably going to use the most. So a times r to the power n minus r to the power of n minus 1 divided by r minus 1. So in this case, S of 5 is, well, the first term is 2. Our common ratio here is 2. We want 5 times, so 2 to the power of 5 minus 1, and r is 2, so 2 minus 1 on the bottom. So here we get 2 to the power of 5 is 32, minus 1. Well, 2 minus 1 is 1, so really this is 2 times 31, which is 62 meters. So therefore, Rhonda has run for a total distance of 62 meters. Okay, so easy extend this question. Let's say that she does this and she keeps doing this for, let's say, 10 times. And so here we're going to know n is 10. We don't actually have to list out all the numbers in that sequence in order to calculate the sum of that. All right, so that's a geometric series. So here's the homework that we can do to get lots of practice on using the formulas and coming up with the different situations in terms of solving for things of a geometric series.